basically. That
Yeah.
maybe your findings are being mildly misrepresented or underestimated or exaggerated in some cases, perhaps?
Yeah, that's what's happening. In fact, both.
Okay, so
As
I'm
these
going
might be.
to introduce you now. So
Sure.
I'd like to welcome Dr. Chirag Dhara. He is one of the authors of the recently published assessment of climate change over the Indian region, published by the Ministry of Earth Sciences in India. Dr. Dhara began his adult academic journey in physics and mathematics at St. Xavier's College in Mumbai, followed by a master's and PhD in quantum physics from the Institute of Photonic Science in Barcelona, Spain. He then went on to earn another PhD in climate science from the Max Planck Institute for Biochemistry in Germany. He's somewhat of a polyglot. He speaks various languages, including Tamil, Spanish, Marathi, and German. We're very fortunate to have him with us today. Dr. Dhara will begin with a short presentation on the findings discussed in the assessment report, followed by a few questions from us. But like you just said, he's also going to put the entire report in context for us. So without further ado, I give it to you.
Thanks so much, Naomi. So let me see what I can do here. I'm going to share the screen. All right. So do you see it?
Yes.
Okay, great. So thanks again, Naomi, for inviting me to do this. It's a pleasure to be here. So this is the book that I'm going to talk about. So once again, my intention is not to get into the details of the book because the book is open access. It's been summarized in multiple places, even within the book, the major findings of this report. The executive summary, for one, is quite a neat summary of the most important findings. Then there are the key findings in each of the chapters, and there are several chapters, which are a summary of that particular chapter with a little more detail than you would find in the executive summary. And then in chapter 1, and these are the list of chapters, so it's quite a detailed assessment of climate change over the Indian region. So the first chapter is called the Introduction to Climate Change over the Indian region, and this one is what sets out the context for global and regional climate change, and what are the major issues pertaining to India in particular. And in this chapter as well, there is a table, a synthesis table, right? It's a last table, I think it's table 1.5, which is also very useful for a general audience because it doesn't quantitatively synthesize all of the results, but it also explains why some of these changes are happening, how they are all connected to each other. So that's the importance of that particular assessment table. By the way, in case you hear any disturbance around me, let me know. I can just shut the door and so on and shut myself inside.
Sure.
So, yeah. All right. So, as you can see, now this book, it's been brought out by the Ministry of Earth Sciences. It was edited. It's been authored by people at my institute where I work, the Indian Institute of Tropical Meteorology. And it's got 12 chapters. By the way, this book was released last week, so it's really very recent. And there are 12 chapters, each one of them focusing on a given aspect of climate, different aspect of climate. So temperature change over India, precipitation, observation of GHG fluxes, trace gases, aerosols, floods and droughts, storms, cyclones, sea level rise, Indian Ocean warming, and the Himalayas, very importantly as well. And then it ends with a small chapter on essentially an essay on climate change impacts that one might expect as a result of all of these changes. Let me get to this particular schematic, which appears in the executive summary. And it covers sort of the most, sought after, if you will, aspects of climate change. So over here on the bottom right, it's the change in temperature over India, all India average. On the left, it's the change in sea surface temperature over the tropical Indian Ocean. Over here is the summer monsoon precipitation over India, how it's going to change in different climate change scenarios. And on the top, we have the results for the Himalayas. So on the right hand side in red, it's the change in air temperature, surface air temperature over the Himalayas. And then we finally have precipitation change over the Himalayas. And I might add, precipitation and snowfall are different things. So what is reported here is annual precipitation, not snowfall in this particular case. All right. Now, what's been reported in each of these cases over here? All right. The chapters, of course, have more detail and so on. So you would have to look into the chapters for more. We have reported for two scenarios. They're called the representative concentration pathways (RCPs), and there are four RCPs that are defined in the literature, and these are basically trajectories of how greenhouse gas concentrations might change in the atmosphere. See, we don't actually know what's going to happen in the future, exactly how GHG concentrations are going to go. It depends on, our energy use, whether we become more efficient or not, whether we reduce consumption altogether. So, there are obviously it's a lot of uncertainty. So what's done in the climate literature is, and still, you need to do something. So what's defined, at least for the previous generation of climate models, they defined these representative concentration pathways, where they defined four different trajectories of changes in greenhouse gas concentrations in the atmosphere. Okay, and they're graded. So the lowest one is RCP 2.6. And what that 2.6, RCP of course is representative concentration pathway. The 2.6 stands for 2.6 watts per square meter of what is called radiative forcing, which is basically just the energy balance, or rather the imbalance at the top of the atmosphere because of a given concentration of greenhouse gases. So uh, under the RCP 2.6 trajectory, your concentrations would be such that at the end of the century, so 2100, you would have what's called the radiative forcing of 2.6 watts per square meter. That's what that 2.6 stands for. And it's basically just the difference between the energy which is coming in and the energy going out. Greenhouse gases, they reduce the amount of energy escaping to space directly. It gets intercepted by greenhouse gases. So that's the difference, 2.6. And then you have RCP 2.6, RCP 4.5, RCP 6, and RCP 8.5. And we've taken two of these. We've not taken all of them. We've taken one intermediate scenario, which is RCP 4.5, and then the extreme scenario, RCP 8.5. Now, one important thing over here is the reason we've taken two of these is that, for one thing, labor intensity. This was a lot of work, this whole report. It was over 2.5 years of work. I joined last year in this effort, but my colleagues have been working for 2.5 years. So one was the amount of labor. The other, though, is that RCP 4.5 and 6, the two intermediate trajectories, these are generally, not everywhere, generally considered the more likely trajectories for the future. Okay, so we chose one of those. And then we chose the most extreme scenario because this kind of is the limiting case, just in case, because RCP 8.5 kind of trajectory of concentrations, that is, we are close to that right now, although it's expected to reduce in the future because of various policy decisions and efficiencies and so on. So if we went at exactly the same rate currently, we would follow roughly RCP 8.5. That's why you will call it, you will read it being called the business as usual scenario. But that is not what is expected for the future. So we have to be very clear about that. This is based on modeling of energy futures, our energy consumption, and what that means for
Sorry, if I
emissions.
may ask you a question.
Sure.
So you're saying not expected for the future if we make changes, if we make
That's
reductions in emissions.
That's
However,
right.
if we continue as we are and we don't make any reductions, then we are on closest to RCP 8.5.
That is correct, but there is not just it's not just about policy. In fact, some argue that we simply don't have enough fossil fuels in the ground to be able to extract and put into the atmosphere to get at RCP 8.5 at the end of the century. So it's both a question of availability as well as policy. Okay. Um, so anyway, so when you say and this distinction is important because what has happened is in all the media coverage that has already happened for this report or even for the IPCC reports. By the way, IPCC reports use the same trajectories. This is based on the same trajectories. They are the same. What happens there is when media covers it is very often the values for RCP 8.5 are quoted without putting it into perspective that this is the most extreme scenario. And in fact, there's a fair bit of um, you know argument to be made that we are it's not possible for us to, or we are not going to actually continue following RCP 8.5 for that much longer. Okay, that's one thing. Now, over the so if you look at this part over here, it's two scenarios, 4.5 and 8.5, and in each scenario we have considered we have reported all of these projections for two different time periods. One is 2040 to 2069. It's a 30-year period. And the other one is the next 30-year period, which extends to the end of the century, 2070 to 2099. Now, the reason for 30-year periods is we want to average out fluctuations. Of course, there are going to be year-on-year fluctuations, right? There's never going to be a steady rise just like that because there's a lot of different processes which moderate temperature, mostly the ocean. So we want to average out some of these variations, and so it's called the climatological mean, which is usually defined over 30 years, or average over 30 years. So that's why you'll see this routinely in climate literature, 30-year periods. Now, these 30-year periods, we are when we report the temperature rise, rather projections for climate models for temperature rise in this sort of average 30-year period, it's reported not relative to pre-industrial times. Now, this is really important. All of these numbers are being reported relative to the baseline period that we've used in this report, and each report can do it differently. The baseline period in this report is 1976 to 2005, 30-year period. Okay. So let me interpret some of these numbers here. So under the RCP 4.5 scenario, we are expecting, I mean, the mean change that is expected from climate model projections, all India temperature rise, is around 2 degrees centigrade relative to the average over 1976 to 2005, not relative to the pre-industrial conditions, which is typically 1850 to 1900. Okay, so in fact, if you compare this with pre-industrial times, took the baseline as pre-industrial, you would have a slightly larger number here. Okay, so that's one important thing. And then, of course, these are climate models, and there are many of these models which are Earth system models, which are run by different independent groups around the world. And you run the same climate change scenario for each of these models, or each group does that. And then they report what are the values they find for temperature rise, et cetera, et cetera. So there's going to be a range between models because, of course, there are a lot of physical processes which are interacting. There's dynamics in the atmosphere. There's changes in wind patterns. There's changes in ocean circulation, atmospheric chemistry. Um, there's the forests, for example, are sinks of carbon. So how these change. So many of these interactive dynamics. So of course, there's going to be a slight range across models. And this is the range which is being reported over here. So the average change projected by climate models is 2 degrees for the scenario, but the range across models is a little bit below that and a little bit greater. So the highest models are reporting around 2.3 and the lower models are reporting 1.7. So that's the way in which to understand all these numbers. And then, of course, this is, you can also think of this as a middle of the century change, by the way. So this is the 2040 to 2069 change. So you can see this as a middle of the century projection. Whereas this, you can interpret this as the end of the century projection. And under the RCP 4.5, what's called the ensemble mean is expected to be about 2.5 degrees centigrade. Now, the RCP 8.5 is a much higher scenario. Okay, there the carbon dioxide concentration is more than four. It's about 4 times as much. Okay, in fact, slightly more than 4 times as much. So there, of course, you would expect the temperature rise to be much higher, and by the middle of the century, it would be uh, about 2.7. That's what we get from projections, and end of the century 4.4. Now, again, let me reiterate. These numbers are relative to the baseline period, which in this report is 1976 to 2005. Okay, so if you see them relative to the pre-industrial conditions, these numbers are going to be higher still. Having said that, let me also reiterate that RCP 8.5 cannot be seen as the trajectory that we are currently on, okay, or rather that we'll continue to be on this trajectory. So reporting these numbers as is and making it sound as though that is what is going to happen is a misinterpretation of because that is not what uh, these climate reports are actually trying to say. They're reporting by the for each of these different scenarios without taking a stand on which of those scenarios would actually come to pass. So that's rather important because there's been some misinterpretation in the media. But anyway, regardless. Now, changes, of course, I spent a little more time there to explain all this context, but then you have the change in the Indian Ocean. And of course, the oceans take longer to warm up. There's a lot more heat content. The ocean has a much higher heat content, and it just takes a lot longer to warm up. So for the same time periods, when you compare changes over the tropical Indian Ocean compared to this, you will find that the rise in temperature is significantly smaller, and that's just totally expected. The way water changes its temperature, it's much slower. Um, but now there's something important that's happening over here, which I would like to mention. These are projected changes. Okay, middle of the century, end of the century. What's also happening is, in the report, what we've also reported is changes in temperature observed to date. Now, the change in temperature over India, we haven't reported it here, but the observed change is about zero point 0.7 degrees centigrade. That's to be compared against the global average of about 1 degree global average temperature rise relative to pre-industrial times. Okay, and for India, it's about 0.7. The Indian Ocean temperatures have risen more strongly. And in fact, the assessment we are providing is that the tropical Indian Ocean has risen by about, temperature has risen by about 1 degree, which is higher than the 0.7 over the Indian landmass. Now, one of the reasons for the muted temperature rise is considered to be aerosols. So basically that's pollution, particulate matter pollution, the same pollution that causes all our health, that has all these health impacts for us, health implications. They also have climatic impacts, and aerosols basically sit in the atmosphere and they reflect sunlight, so they allow less solar radiation to reach the surface, and so of course there'll be a relatively muted temperature rise because of which otherwise would happen in their absence. So the over India, of course, the aerosol loading is quite large. Now is an exception, but in general. And so it's considered widely understood that aerosols have offset temperature rise over India, and it could be as large as half a degree. Having said that, very important, aerosols are very tricky business. Very tricky because they interact with climate in multiple ways. There's a direct effect where they directly interact with solar radiation coming in, but there are very important indirect impacts, effects on climate, where they also interact with cloud formation. So they change how clouds form to the extent that they form, where they form, and so on. So there's a lot of uncertainty, a lot of work ongoing about the impacts of aerosols on global climate and by the way, you can read these in the IPCC reports as well. There's a huge amount of uncertainty when it comes to aerosols. But in general, it's considered that aerosols have offset a part of the temperature rise because of greenhouse gases, which would have happened in the absence of aerosols. Aerosols also have an effect on precipitation, on rainfall. So let's go to the rainfall aspect here. So once again, the two scenarios, two different time periods, middle of the century, end of the century. Now, India's observed change in India's rainfall appears to be a decline. There's been a decline in India's total magnitude of summer rainfall, by which I mean June to August rainfall, June to September rather. The assessment we've got is from 1950 to 2015, there's been a 6% decline in magnitude, total magnitude of India's rainfall. However, for the future, okay, before I go to the future, now the decline, why is there been a decline? That's the important question, because of course the rainfall is absolutely critical to all of us living here on the subcontinent. One of the major reasons is appears to be aerosols. In fact, the aerosol loading over the subcontinent. Like I said, aerosols, they suppress temperature rise. They also suppress precipitation. That's the general understanding. There are other factors at play as well. Of course, not all of the decline in rainfall can be attributed to human-induced climate change. So by no means is that the case. There's also a lot of natural variability, particularly in rainfall. Right? But then there's an increasing body of literature now which understands this decline as aerosols having a role in this decline. There are other factors, other anthropogenic factors, and one of those, although much more evidence is needed to really have an element of more certainty, I suppose. Irrigation. More intensifying irrigation is also considered one of the mechanisms by which potentially there's been a slight drop in India's rainfall. It's ironic, really. So in any case, what climate models are projecting for the future is that there's going to be a rise in precipitation. Okay, so the strength of the Indian summer monsoon, and it can be quite strong. So under the most extreme scenario, the mean of the model projections is about 14%. But there's a huge range among models when it comes to precipitation. Okay, so while the mean might be 14, look at the range. It goes from 10% rise to 22 or 23% rise across models. So, and a lot of this has to do with uncertainty with clouds and cloud radiative forcing and things like that. Okay, so a lot of work is going to be required, and in fact, this is one of the messages we also, because one of the things we also focus on is knowledge gaps. Because of course there's so much we know, but then there's a lot that we don't know as well. it's an evolving field. And studying aerosols and its effect on climate and how the Indian monsoon is going to respond to all of these different drivers is one of the major um, uh, aspects that requires a lot more intensive study. Um, what else can I say? Um, all right. So yeah, you can just, look at this, for example, this is an extreme case really. RCP 4.5, sort of mid-century values, the mean of the projections is 6% rise, by the way, relative to 1976 to 2005. That's the baseline period. All of these numbers are relative to the baseline period. 6% rise, but then there are some models which are actually projecting a decline in rainfall, whereas others are projecting a 10% or 11% increase in rainfall. So, there is quite a lot of range between models. Now, the reason for a rise in precipitation in general, the physical mechanism, is increasing moisture. As temperatures rise, the amount of moisture in the atmosphere increases. I mean, warmer atmosphere, warmer oceans, so more evaporation into the atmosphere. And that's really the physical mechanism, basic physical mechanism why a rise is expected with warming. And this is globally, by the way. Globally, for certain, you expect a rise. Regionally, there are always changes because there are so many more mechanisms which act, particularly on the Indian monsoon, which is one of the most complex climatic phenomena in the world. Um, it's it's um, it's the strongest monsoon system in the world, and it has both remote drivers and local drivers, and more local drivers and remote drivers. So yeah, so it's a combination of all these that's tugging at the monsoon in different directions. Um, Changes, then of course, we've reported changes in the Himalayas, both in precipitation and in temperature. Let me comment on temperature changes first. If you compare these changes in temperature with changes, all India average changes, you'll find that increases in temperature are higher in the Himalayas. There's a phenomenon called elevation-dependent warming. Okay, so there are some feedbacks which apply in sort of these glacier-covered uh, high altitude parts of the world, which don't really apply to sort of sea level or lower altitudes, or not covered by ice or snow. So because of that, there is this elevated warming rates. And in fact, the observed warming observed today compared to pre-industrial times is well over 1 degree in the Himalayas. Well over. I mean, to the, 1.2, 1.3 degrees. And also for the future, the same thing is projected. It's going to rise faster uh, compared to the rest. And of course, the Himalayas is a very biodiverse, very delicate ecosystem. So that's of a lot of concern.
Can
Over
we
here, sorry, yeah.
Can we just jump in because you
Sure.
talked of precipitation and then we have a question. So when you say
Yeah.
precipitation is going to increase, that means rain is going to increase. Is it going to increase uniformly all over India? Are there parts that are going to face extreme drought? And then we know this, right? There's going to be extreme rainfall and extreme drought.
Yeah.
So
Yeah.
are we talking about, because when you talk of your baseline period, would you characterize that as fairly stable climatic conditions? I mean, as good as it could have gotten for us?
No. So when we talk about these precipitation changes here, this is just the average over India, but it says nothing about its distribution. Distribution is, in fact, there's more agreement among models that precipitation will become more variable with climate change than there is agreement among models about exactly how much the average precipitation will rise. Okay, So distribution, this rainfall will not be well distributed in either space or time, or rather, okay, let me rephrase that. It'll be less well distributed, both in space across the country and in time, meaning different years, than it was in the pre-industrial conditions. Now, the thing you raised about the baseline period, um, when we talk about a baseline, we are not saying that the baseline period is good conditions in some sense. That's not the implication there at all. It doesn't mean that climate hasn't already changed in the baseline period compared to the pre-industrial times. It has. The baseline periods are chosen for very many reasons. In fact, these can become topics of great debate. And in fact, for the next IPCC report, the baseline is going to be different yet again. It's going to be 1986 to 2015. One of the reasons to choose these baseline periods is because of the way climate simulations are done. So you have what are called pre-industrial control simulations, then you have what are called historical simulations, and then you have simulations for the future. What we mean by historical simulations is that, see, you need to benchmark these climate models. Okay, so you need to check if these climate models are getting observed climate correctly, or within acceptable bounds. And so they simulate climate from 1850 until for the previous generation of climate models until 2005, and for the next generation of climate models, the upcoming ones, they will simulate up to 2015. And so one of the reasons to choose the baseline period such is you're taking the last 30-year period of your historical simulations. For the previous generation, that the last 30-year period would have been 76 to 2005 because they end in 2005. For the next generation of models, it ends in 2015. So you take 1986 to 2015. So that's the logic for choosing baseline periods. Not that the baseline periods were, some kind of a model climate conditions to compare against.
So every time we talk of a temperature increase, we're talking relative to the last 30 years?
We are talking relative to the baseline period. That may be the last 30 years, but you always have to check this. It's very confusing, even for us. Whenever we see a temperature rise reported in any report, you always have to look for, is it relative to, which baseline period is it relative to? One example. Many of you, possibly all of you, are aware of this IPCC special report on 1.5 versus 2 degrees warming. That 1.5 and 2 degrees is relative to the pre-industrial baseline, not recent 30-year period baseline.
So how much have we increased relative to the pre-industrial times in terms of temperature?
In India?
In India or globally, both actually. If you can
globally, the estimate is about 1 degree. And over India, what we've assessed is 0.7 degrees. And like I said, 0.7 is less than the global average of 1 degree. And one of the reasons for that muted temperature rise is aerosols. Because there's a lot of aerosol loading over the subcontinent.
All right.
Aerosol concentrations.
Because you brought up precipitation, I just want to quickly ask you this before we jump to something else. Because I also want to ask you about feedback loops and how, if that's been factored in, but I'll wait for, for a bit to ask you that. But this variable precipitation, so basically irregular rainfall, either we're going to have very, very heavy rainfall in some areas, extreme drought in other areas, and we're not going to be able to basically judge what kind of rainfall we're going to have when, unless our meteorological department becomes supersonic in some way. How do you think that's going to affect sort of the social fabric of any region? If, say, a country is made up of several states, like for instance, the US, and some states are in extreme drought while other states are receiving extreme rain, how do you think that affects the social fabric and also the water and food security of that country? If you just want to have like a general view or a broad view on that, if you want to share
that. I'll start with a disclaimer, to save my skin as much as anything else, which is that this question, of course, is now what I'll say about this question is going to be my view, personal view, not what we've assessed in the report, because the report is all about how things are going, how things have changed, why they've changed, and how they are expected to change according to climate models. Okay, so these are the physical science aspects are what we've assessed. Now, this question I'm going to sort of respond as my personal views. Now, of course, given all these changes and given how central precipitation is to the country, having a uniform of both food security and water security, you would of course expect some major issues. I mean, we've already had lots of problems in various parts of the country over water sharing. And if you have more variable precipitation where some states are going to start grabbing more of the water which earlier they didn't have to from rivers, say, or start damming rivers without agreements with um, neighboring states and so on. Of course, that's going to create a lot of trouble. Kerala blamed Tamil Nadu for some of the flooding issues because they said dams were opened without warning and so on. So, of course, these are issues that will come up, and we have to adapt. Firstly, we need much more scientific work on regional changes because even our report has not dealt in detail with very small scale or local scale changes. The reason is we are simply not able to right now. Climate models, um, we need a lot of, the more local you go, the more difficult it is. And there's simply not enough scientific literature yet to be able to deal with those issues in a satisfactory manner. So all of the studies are for larger regions, or say the central part of India, which is critical to our agriculture and so on. So what are the changes going to be? Now, some of those changes, of course, are, by the way, reduction in rainfall has been much more so in the Indo-Gangetic plains, where a lot of agriculture happens. So, and very high population densities. So, when you have these larger changes in highly populated areas of the country, you would expect much more impacts on people, on infrastructure, and so on. Of course, if it happens in the South Indian, southern part of the Indian Ocean, well, we are not going to see impacts here, are we? So impacts really depend on the context, not just of the changes that are happening, but also demographics, vulnerability. So I most certainly expect that these changes are going to lead to large impacts if we continue like this without adaptation. Mitigation is another matter entirely, but we need to adapt. Okay. Um, shall I? Is there more we can discuss on this, or shall I move back to this?
Yeah, go ahead and move back. But I do have a question on temperature increase and feedback loops, but I'm going to ask you that at the end or when it seems appropriate again.
Okay, okay. So I'll continue and then we can. Is that a question over there?
Yeah, I'll try to ask you the question. The point is that in terms of water security, given the disproportionate precipitation that we are seeing in various parts of the country and the agriculture systems dependent directly on them, we need headway to do water management in terms of even adaptation or mitigation in some ways, because it is going to rain. It's probably going to rain the worth of 1 month in 1 hour or something like that. And is there anything being done where the government is working with the Met Department, where we are working towards mitigation of these kind issues, where we have a 4-year headway into this, or is it going to be decided after a point of no return? And that would be detrimental, especially because I'm assuming if there is a constant temperature rise of 0.7 to 1, even in the Himalayas that you were talking about, then we are going to run out of the river water in some ways, or political issues will probably clamp that down. So I'm just looking at how do we have a conversation in the future in terms of working towards this from now itself with the data that we have, regardless of what the outcomes probably might be. And if there is any work, then there.
I think I'm going to answer that in one line, which is when you say is this happening? I would say I hope so. moving on. So temperature, I mean, moving on, unless there are other questions, I'm happy to sort of engage with Q&A at any time, by the way, so feel free. If not, I'll go back to this. So temperature change over the Himalayas, like I just said, it's higher because of these elevation-dependent warming effects. Some of the other this one here. This is also something I would like to. There are one or two issues I'd like to draw your attention to. Change in annual precipitation over the Himalayas, and this is percentage change, by the way. This is precipitation, not snowfall, and the precipitation for reasons similar to India's overall precipitation. We expect the precipitation to rise over the Himalayas, but snowfall, both observed and projected, is expected to decline. Okay, snowfall has been declining in the observed period. Now, warming is one of the obviously one of the major reasons, but there could also be internal variability which is causing that to happen. Glaciers are shrinking. Now, this is not on this slide, but it's part of the assessment. Glaciers have been shrinking in much of the Hindu Kush Himalayas, but in the Karakoram ranges on the east, declining snowfall has been compensated for by what's called the Western Disturbances, which are these massive weather systems that make their way all the way from the Mediterranean up to here. And they bring a lot of moisture, and they've been dumping it in that part of the Himalayas. So what's happened is there's been a compensation effect where there's been no observable glacier loss, mass loss in the Karakoram Himalayas. Okay, unlike the Hindu Kush where there's been clearly observed glacier shrinkage. How much is a difficult question to a certain degree, because Himalayas, the observation systems are relatively sparse and so on. So how much glacier shrinkage and so on is a harder question to answer to make that precise. So those are some of the major things. Back to precipitation. Extreme precipitation events are expected to increase very rapidly, by the way, very substantially. In fact, even in the observations, we've seen a threefold increase in extreme precipitation events over central parts of the country, which is what is called the core monsoon zone. And this is something which is a fundamental manifestation of climate change. There's no two ways about that. And one of the reasons for extreme precipitation is the amount of extra moisture in the atmosphere. So when there is when there is a lot of rainfall, there's just much more moisture to rain out, and that brings us much heavier precipitation than before. For the same reason, we would actually expect, and this is globally the case, we would expect a greater fraction of precipitation, okay, of rainfall to come down as extreme events than before. Now, the reason there is that average precipitation rise is growing slower than the amount of moisture in the atmosphere. Okay, the amount of moisture in the atmosphere is expected to grow by about 3%, or less than that actually, about 2 or 3%. What did I say? Did I say amount of moisture? Yeah. So the amount of moisture is expected to grow by about 7% per degree rise. Okay, but the amount of precipitation is only expected to grow by about 2 to 3% per degree rise in temperature. Okay, and remember that extreme precipitation depends on the amount of moisture. So you expect extreme precipitation to become stronger and become a larger fraction of how precipitation comes down. Okay, and because of that, you will have a lowering of the amount of rainfall that comes in more well-distributed rainfall, as more well-distributed rainfall, which means more dry period. You'll have a better distributed rainfall with larger dry periods followed by very extreme rainfall. And this is just globally the case, and the physics behind that is relatively elementary.
So, I mean, as a layperson, to me, that would affect food security, because
Oh, absolutely.
if fields are flooding or you don't have enough water, neither conditions are great for growing food.
Absolutely, absolutely. Our crops require well-distributed rainfall. As I mean, both. Ironically, you have a huge rainfall. Very extreme rainfall. It can destroy crops. You have an extended dry spell that can affect crops, or you have larger interannual variability, meaning year-on-year variability that affects crops. So, regardless of having a lot of water, of course, isn't great. And of course, if you have same thing with groundwater. So water security. You have extreme rainfall, especially in deforested areas. The water flows off rather than getting seeped into the soil because it just is so hard. So it doesn't. It's not good for groundwater seepage. Very dry events are not good for groundwater seepage. Uh, Drier soils that would go with higher year-on-year variability in rainfall or these long dry spells also means drought periods. Okay, longer drought periods. Um, Now, one of the things is let's take precipitation. Under this extreme scenario, and it says it's going to increase by 8% or 14% and so on. That doesn't necessarily mean that drought conditions are going to ease. And the reason for that is your precipitation might increase, but given that your temperature has risen significantly, 2.7 or 4.5 degrees centigrade, your evaporation from the soil also increases very rapidly. The rate of evaporation increases rapidly. And that can, in fact, overcompensate for increased precipitation.
Can we put a
So you might have a lot of precipitation.
Sorry, can we put a time context for what we're talking about? Because when you say 4 degrees, then we're talking 2100, I'm assuming, extreme case.
That's right.
So
That's right.
could we maybe talk about what we can expect to see over the next 20 years? Just sort of an educated sort of projection guess.
So, for that, no, that's a very, very important, very good question to bring up. In terms of which scenario for changes in greenhouse gas concentration will follow, I would look at more the RCP 4.5, which is these here, or the RCP 6, which we have not covered in this report, but they're there in the IPCC reports. So somewhere along those lines. So, between, let's say, middle of the century, 2 degrees. See, middle of the century, RCP 8.5 is 2.7. So RCP 6, roughly speaking, it would be somewhere in between, so between 2 and 2.7. So let's say about 2.4. So between 2 and 2.4 degree rise, relative to 1976 to 2005 average, is what we would be looking at in the next 30-year period, okay, by 2050-ish. And you can apply the same logic more or less to all the other numbers you're seeing here. Now there is a certain very important issue which we have not discussed in the report because it's or the IPCC reports because they're very hard to quantify. The concept of tipping points. Tipping points are very abrupt changes in the climate system, which can trigger an irreversible change, a very rapid irreversible change. Okay, and there are a lot of tipping points that have been identified, and the problem with tipping points is we don't actually know where they are. Okay, I mean, meaning for what rise in global temperatures will be trigger a tipping point, which will cause an extremely rapid change in increase in temperature. Many of these tipping points are all accelerating temperature rise. If we trigger them, we might very rapidly, much more than the relatively smooth rise in temperature we've seen so far, we could suddenly trigger a much higher rise in temperature. And it could become a cascade. So some tipping points, when triggered, cause this very abrupt jump in temperature, which itself could trigger other tipping points. Now, when might we see such tipping points being triggered? Over the years, over the decades, maybe I should say, we can only, in a certain sense, we can only make an educated scientific estimate for where these tipping points lie. It's very, very hard to quantify. Earlier, in the first few IPCC reports, it was considered likely only, triggering a tipping point was considered likely only if we cross 3 or 4 degrees of global temperature rise. In the most recent IPCC report, there are lots of IPCC reports, special reports coming out, but the most recent, meaning the special report on 1.5 versus 2-degree warming. Since that report, there's been a lot of scientific literature which is discussing possible triggers, tipping points being triggered between 1.5 and 2 degrees centigrade of global temperature rise. So far, we've not got there, but we are in danger of locking it in the next 10 years, 1.5 at least. And if those are triggered, we might see a much more abrupt temperature rise. So when we talk about these, this 2-degree rise, let's say this 2-degree rise under RCP 4.5. If we trigger tipping points, and especially if we trigger a cascade of them, we might see a jump over this 2 degrees, but it's hard to quantify that. So this is a conservative number in that sense. Yeah.
So, okay, so I just want to recap. So by 2040, based on RCP 4.506, where will we be in terms of temperature?
Let's say 2050, between 2 and 2.4 is what I would say.
Okay, and does your model take into account any of the feedback loops or any of these tipping points going off before then? Or is it just purely based on what you saw 30 years prior, and then there's a projection given emissions or given the emissions trajectory, and that's how you've made your predictions?
There are two different things. One is feedback loops, and the other one are tipping points. Climate models, they include feedback loops as we understand them. All of the feedback loops that we know of and we understand, they don't include tipping points.
Does anyone else have questions? Now would be a good time.
Yeah, the question that I have is that can you tell us a little bit more about wind systems, if that makes sense? Because if we are in the tropics, and this is my layman understanding of science, we're going to have evaporation, as you said, and quicker evaporation, especially at the surface level.
We are going to have what?
Quicker evaporation.
Evaporation, yeah.
Yeah. And so if like, is there anything that we can identify as wind systems change? Is there any things that we can identify on which are the parts that it is going to rain? And especially also understanding the fact that it's not just about groundwater, the rainwater also brings in minerals along with it, which is necessary for plant consumption. And so this wind system and how it collapses in general, is there a trend to this, or is it completely arbitrary and we have no understanding of where? Because then we can then think of possible geographies that we might relocate ourselves for kind of having a safer future in some ways, without giving into these geopolitical conflicts that are going to rise and migrations and things like that.
Yeah. So let me try and understand this correctly. So you're asking, please correct me, okay? You're asking how we understand wind patterns might change in the future. I'm assuming you mean it pertinent to India? Okay, kind of, or in a larger sense, let's say. And where we might see the greatest impacts that we can try and avoid being in. Is that how I understand your question?
Try to avoid where we are being in, but also from a restructuring perspective of like, because infrastructure won't be built in 1 year or 2 years, it's going to require additional satellite infrastructure to be built first, and then transition to peri-urban, then transition to like secondary B towns, and then them flourishing. And then we're looking at a complete breakdown of the city model in terms of collapsology, where people won't stay here because for the availability of water is my fear. Now, if we can understand from the wind patterns where it's going to rain, then probably there might be worth in figuring out where can we mobilize and how can we reorganize ourselves.
Okay.
Without being solutionary, I know that like you're a scientist and you want to take that approach, and I don't want you to give me solutions, but give me directions towards thinking.
Yeah. That is a difficult question to answer based on the current science, which parts of the country might be affected most, and precisely what changes we might expect in different parts of the country. There are some indications, but the science of the monsoon is simply not precise enough to say that 30 years from now, this part of the country is expected to be much more affected than the other part of the country. So it might make more sense to put out infrastructure, if possible, over there. As to wind patterns, what is generally expected is that the monsoonal winds that bring rainfall to the country during the June to September period, they're actually going to weaken. Okay, but rainfall is going to rise nonetheless. And the reason it will rise anyway, despite the weakening winds, is because of this increased moisture content of the atmosphere. Okay, so if the moisture content didn't increase, if the winds had reduced, you would expect a lower. I mean, the wind, the magnitude of wind speed and so on had reduced. You would expect a decline in the monsoon. But the sort of winds becoming of lower strength, but precipitation rising, it's going in opposite directions. And the difference there is moisture content, which rises very fast.
And can that be compensated with forests? That's my additional question, because I see no ray of hope in this. It feels like it's completely arbitrary, but I hear that forests capture moisture. So would that make sense in terms of pulling in moisture and then forcing rain instead of doing a rain dance?
Yeah. I mean, in general, one would expect that having a significant increase in the amount of forested area would certainly assist our precipitation. Yeah, because for example, look at one mechanism. Suppose we have a lot of rainfall. What forests do, for example, they take that water and they don't allow it to run off, and it percolates much more into the soil in wooded areas. And then the other thing that trees do is they grab the water from the soil and put it back in the atmosphere as they draw it. It's called evapotranspiration. So they're transpiring. And that, of course, puts more moisture in the atmosphere, which can drain out again. So of course, afforestation is one of the safest, best, cheapest means we have for climate change mitigation and adaptation. There is just no two ways about it. Carbon capture, maybe it works, maybe not. Do we bet our survival on it? What we know for certain that has worked for millions of years is trees.
So I just want to clarify, do you mean afforestation or reforestation? As in expanding existing forest or putting forests where they recently were, or like going in and planting trees where there never used to be any, like for instance, planting trees on a grassland? Are you recommending that, or are you recommending reforesting or sort of expanding existing forest? Because the soil and the bacteria in the soil would be helpful to that process.
Others would be better placed than me to, ecologists would be far better placed than me to take that question.
As in when to put the forests, but you're saying more trees in general would be.
Yeah, in general. But of course, primary forests by far are the most important when it comes to stabilizing the climate. I mean, new trees, new plant saplings, they certainly don't have anywhere near the same capacity for as a primary forest, virgin forest, which has never been chopped down. So having forests, having trees where they used to be originally is the most sensible way to go.
So
So protecting what you have.
if I was
And
prime minister for a day, or just in general, prime minister of any country, and I was coming to you and saying, I want to do something, to safeguard our future in terms of the environment, but I want to cut down XYZ forests, would you advise against that, or?
what I would do is to refer you to Madhav Gadgil.
Sorry, you would refer me to?
Madhav Gadgil, Professor Madhav Gadgil.
Okay.
There are few people who are as much an expert on India's ecology as him, and the amount of work he's done is phenomenal. So I would beg off that question and divert it to Madhav Gadgil.
Fair enough. Fair enough. But okay. All right. Let's move on. Do we want to go to the next subject possibly?
Oh yeah. In that case, let me go back to the question that Sabzi asked me. That's what I read on his profile. So I'm going to call him that. Um, I think when it comes to infrastructure, what I would be more concerned about right now, which we have more control over, more knowledge of, is sea level rise. Okay, so there's a lot of India's infrastructure, not to mention irrigation and so on. Uh, Including, when I say infrastructure, I'm talking about power plants. I'm talking about roads. I'm talking about these coastal roads that are coming up. I'm talking about monuments and so on, both that are essential as well as non-essential. They're being set up in coastal areas. And sea level rise is one of the major problems that's affecting us. There's much more certainty there as well. So coastal infrastructure, especially, they are expected to last 30, 40 years, perhaps more. They have to take into account sea level rise. On the eastern seaboard, on the eastern coast, there's also a threat of cyclones. And sea level rise combined with cyclones, combined with increasing moisture in the atmosphere, just makes for much fiercer storms with much greater wind speeds and much greater precipitation and much greater inland inundation. So any infrastructure which is built now without taking all of these projections into consideration, um, then why are we doing this work?
Open up to other questions. But when we talk about like sea level rise, sorry, I know I said other questions, but I just have one. We're talking like sea level rise in mm's, right? In like millimeters. We're talking sea level rise in like millimeters, increments of what, 3 millimeters a year? That doesn't sound very significant to like most lay people. What is 3 millimeters is almost nothing. So what does that translate into in terms of, can you give me an example of how that would like affect us?
Let me do one thing, which is actually this is something I discussed in. You can still see the slide, I think. You can you still see the presentation or what? Or can you see my screen itself?
I can see your screen, unless
I can see the presentation. Now it's gone.
Yeah, just give me a second. Let me just share, to answer that question, let me share a schematic that I made for an article I once wrote. So that really does a good job, I think, of. Just bear with me for one moment. Sea level rise, figures, graphics. Yeah, I think this is something I can use to discuss this question. Okay, so let me share my screen again. Here. So can you see this?
Sure. Yes.
Yeah. So what we're looking at here is the amount of additional inland intrusion of seawater with sea level rise. So let me walk you through this. Okay. So imagine that you had a sort of what we call an original sea level, some baseline, which sort of intersected with a coastline over here. So this would have been the earlier coastline. Now, sea levels are rising at about 3 millimeters globally and also on the Indian coast, but about 3 millimeters per year. So in 10 years, you would see a 3 centimeter rise. Just multiplied. So 3 centimeter rise in 10 years. So now this is your new sea level. Now, as it happens, see, imagine that your coastline was simply a wall, okay? In that case, your sea level rise would just go from here to 3 centimeters higher. The thing is, the coastline is tilted. And in fact, that slope is very, very gentle. And because of that, your inland inundation is much, much larger. Okay, so for a 3 centimeter rise like that, for a very gently sloped uh, coast, your additional inland intrusion would be about 17 meters for just a 3 centimeter rise. So that's why what might seem like a small rise in vertical sea level, when you translate it into inland intrusion, can translate into a lot depending on the slope of the coastline. And for example, on India's eastern coast, in the river delta regions, your coastline is very, very gentle. And the elevation is very small over sea level in general. So, even what might look like a small sea level rise, it can go inland a lot. Take a cyclone. The storm surge from a cyclone, it shocks me when I think about it. It goes kilometers inside. It can go up to 20 kilometers inland, a powerful cyclone. So that's the kind of, would you think it? Would you think that without sort of knowing these numbers, that storm surge because of cyclone can intrude by 20 kilometers inland? It's a crazy number. So the same thing, small changes can lead to large impacts. Yeah.
But in the dikes system in Netherlands, for example, they have been fighting for the last 50 to 60 years against intrusion of water. We have been doing reclamation. We probably have more powerful equipment now to build our, coasts back with money that some governments can put in and some governments cannot put in. And maybe some will benefit and it will keep on eroding. And this is a constant battle. But any kind of infrastructure that I feel right now, even if it is in the format of like creating khazans or creating like alternative salt marshes, a barrier between coming in for this intrusion, especially for this higher tsunami kind of events or like really intrusive water coming in. I feel no, my question is that then do you think that that kind of coastal infrastructure is still worth it, especially given the way that anomalies, which science we don't have quantification of, is there any point of even trying to do coastal mitigation, or are we just going to say, guys, stilts or get away?
Yeah. I think a combination is, as with many of these things, one stop solution will never work because regionally sea levels are rising at different rates, even across. Indian coastline is about 7,000 kilometers. Sea level rise is not uniform everywhere. Sea levels rise for various reasons, including not the sea at all, but because of the land. So in parts of the country where sea levels are not rising too fast, you could probably get away with barriers. In other parts, very low-lying areas where sea levels are rising relatively fast and very fast, in fact, maybe you need to start considering pulling back infrastructure and pulling back people from those areas. In fact, people have written articles arguing just that recently.
Could you, off the top of your head, do you remember anyone that you could recommend an article that we could read on that?
Yeah, Anurag Dando, Danda, but being Bengali, I think it would be Dando. Dr. Anurag Dando, he works for the World Wildlife Fund. He's based in Kolkata, one of the experts on the Sundarbans over there. He writes very insightful articles, so including on this aspect, which I read recently. I think it was him. His articles I really recommend reading. Anurag Bandu.
Uh, okay, and also you think the East Coast is more at risk than the West Coast of India, or because we recently saw these articles of like how Mumbai will flood by 2050 and what have you.
Yeah.
Do you think that's an exaggeration, or do you think there's any truth to that, or that's something we should pay heed to and maybe think about when investing in real estate or what have you in the city?
Um, that particular study you're referring to, there has been some pushback from Indian scientists. Um, so I haven't read the paper carefully myself, so it's a little hard for me to take a committed stand. What they've done is they've used, so they haven't changed so they're not, the paper, the thing that was different about that paper, why it gave much more scary forecasts for how sea level rise will affect us through flooding, is not because they're saying sea level rise, the rate of sea level rise will be different. What they're saying is that the earlier climate models didn't have the topography. And what they're saying is they've got a much better digital topography of the world. And according to that, the same amount of flooding you would expect from the same sea level rise is more. That's what they are saying. Now, of course, these maps, when you develop these maps, they could be better for some parts of the world than for others. So how good it is for Mumbai city or other cities along the Indian coastline is something which, through peer review and so on, you need to determine. Taking a single paper is never a good idea. In fact, and that's why we call this an assessment report. When we do reports like this or the IPCC, this is the report that we are discussing today is the regional analog of the IPCC global scale reports. You take multiple lines of evidence, as it's very fancily put. Okay, so you take a lot of different climate models, you take a lot of different independent observations, the entire body of scientific literature, paleoclimate data, and you put them together and see as where they agree, where they disagree, and what is the emergent picture instead of relying on one paper. So I would not necessarily put store by any one paper, whether this or any other paper, by the way. This applies across the board. But it is certainly a matter of concern, grave concern, that they're saying that according to their new study, new digital topography, that flooding could be a much more severe problem than earlier recognized. So I think it is to be taken seriously, maybe not literally. I can't hear you. You're muted. Can I have one moment? I just want to get a sip of water because my throat is going dry. So give me 1 second.
Does anyone else have? Oh,
You can pause the recording and then restart if that works.
Yeah, back. Yeah.
all right. I think that about. I guess I want to just ask you, like, to put it in words, because just to make it easy. When do you think? You said earlier that we may not be locked into 1.5, but I've read reports where they say that we've already put in enough greenhouse gases in the atmosphere to lock into 1.5 relative to pre-industrial levels. So is that true? Because when you say 1.5, do you mean relative to your baseline period, the one that you've selected in your report, or relative to pre-industrial levels? Relative to pre-industrial levels. So we haven't locked in enough greenhouse gases to cause that kind of heating already.
That's what the most recent IPCC report says. Okay. And by most recent, I mean the special report on 1.5 degrees that appeared in end of 2018. That's what they're saying. But they said what they're assessing based on, again, a wide range of literature, is that in the next 10 years, if we continue putting out fossil fuels at this rate, we will have locked it in. That's their assessment. IPCC reports can be a little conservative. Okay, so there is always that possibility because the way these reports are done, especially the IPCC, which is at least hundreds of authors, if not 1,000 plus, they have to come to a consensus. Okay, and this consensus building is a fractious process. People have to agree. Even if their papers are being challenged in the process, they have to agree to the final draft. So IPCC reports can be conservative. We have to keep that in mind. So at this time, I would go with this IPCC analysis, but I would not bet on it. I think we have to reduce our emissions much faster. We shouldn't even wait for 10 years. Why should we? We are betting our lives on it. So
50% chance.
50 or 66% chance and so on. Exactly. Absolutely. That's great that you got that up. Yeah, it's not even, it's a relative, is it 50 or 65%, 66%?
I'm not from IPCC, so I'm going to say 50.
I think I read 50, but
50.
It depends on what we're talking about because different reports say different things.
That's true. So, even if we've not locked in 1.5, and my judgment would be that not yet. If we completely stopped emissions today, I think we've not, from what I've read so far, my impression is we've not locked in 1.5.
So if we went to zero emissions tonight,
yeah,
we went on the news tonight and we said, that's it, no more emissions. We
Yeah.
would not hit 1.5 centigrade temperature increase relative to pre-industrial levels in the next 10 years because carbon shows delayed warming at least by 10 years.
More likely than not, to use IPCC's terrible language, we would not.
Okay. So your assessment by 2030, roughly, based on what you've seen in the findings of your report, by 2030, what temperature will we likely be at? Obviously, we're not like locking you down, but likely.
So, again, educated guess. Relative to 1976 to 2005, that average, not pre-industrial, relative to that average, I would estimate between 2 and 2.4 degrees centigrade.
By 2030.
Oh, 2030. Oh, right. I was thinking 2050. 2030. Close to 1.5 for India. Oh, God, this is very complicated business because aerosols, in particular, over the subcontinent, play a very significant role. So if aerosols got removed, the temperature jump could be higher.
And aerosols also come from our dirty coal, right? Like when we burn coal for electricity, that releases aerosols.
Possibly.
Right.
Yeah. So, very rough guess, I would say 1.5, probably more.
By 2030.
Of the aerosol effects by 2030. Yeah.
If we remove
over land. And please remember, this is over land. The 1.5 degrees is land and ocean combined. The global rise 1.5. Whereas over land, we have already at least touched 1.5 over land alone. So even if the global mean will not touch 1.5, suppose we manage to make it so, land temperatures might still exceed 1.5 because temperatures over land are higher.
Okay, that's pretty clear for me.
Yeah.
All right.
So I would estimate at least 1.5 over the Indian landmass, possibly more. Educated guess.
By 2030. Educated guess. Okay. All right. Thank you, Dr. Dhara, for your time and for everyone who joined. I'm going to stop recording now. We can sit and hang. We have this room for another 30 odd minutes, but I'll stop recording now.